You know that feeling, right? You reach for a doorknob and zzz, a tiny spark. Or maybe you pull off a sweater in a dark room and you see those little crackles of light. It's this mysterious force we all run into, an invisible energy that can be kind of funny one second and absolutely terrifying the next. Well, today, we're going to make that invisible force visible. So think about it. What on earth could possibly connect that little zap from your finger with the awesome, just destructive power of a lightning strike? I mean, they seem like they're from completely different worlds, but here's the spoiler. They're not. They are fundamentally the exact same thing.
And there it is. The answer is static electricity. And no, it's not just about your socks sticking together in the dryer or having a bad hair day. It is a fundamental rule of physics that works on a tiny microscopic scale and on a scale that is just magnificent. So let's peel back that curtain and really see how it all works.
To really get what's behind that zap, we have to start small. I mean, unbelievably small. We're talking about going all the way down to the level of atoms, the basic building blocks of, well, everything. It all kicks off with something called electric charge. The best way to think about it is that it's just a basic property of matter, kind of like mass. And it comes in two flavors, positive and negative. It's this charge that creates an electric force that can literally push and pull on things without ever touching them. So, inside every atom, you've got this little family of particles. In the center, in the nucleus, you've got your positive protons and your neutral neutrons. But here's the star of our show. Buzzing around the outside are the tiny negative electrons. And this is the key to everything. Those electrons are lightweight, they're mobile, and they are ready to move. They're going to be doing all the heavy lifting in our story. So, the whole game is about balance. See, when an object has the same number of protons and electrons, all those positive and negative charges cancel each other out. It's neutral. But if it loses some of those speedy little electrons, it suddenly has more protons left over, and boom, it's positively charged. And on the flip side, if it grabs some extra electrons from somewhere else, it becomes negatively charged. So how do all these charged objects actually interact with each other? Well, it all boils down to one beautiful, simple rule, the law of electric charges. You've heard it before. Opposites attract, so a positive and a negative will pull toward each other. But things with the same charge, two positives or two negatives, they push each other away. They repel. Seriously, this one simple rule explains everything we're about to see. Okay, so we've got the basics. We know what charge is, and we know the one rule it follows. But how does this whole imbalance of charge even happen? How do we get those electrons to actually pack their bags and jump from one object to another in the first place? Well, the most common way is just good old-fashioned friction. I mean, we've all done this, right? You run a plastic comb through your hair. At the start, both the comb and your hair are neutral. But that rubbing action literally scrapes electrons off of your hair and onto the comb. So now your hair, having lost electrons, is positive, and the comb, which gained them, is negative. It's that simple. But wait, how do we know which way the electrons are going to jump? Is the hair going to lose them, or is the comb? Well, that's what the electrostatic series is for. It's kind of like a cheat sheet. It ranks materials based on how tightly they hold on to their electrons. Stuff at the top, like your skin, gives them up super easily and becomes positive. But materials down at the bottom, like rubber or plastic, they're total electron grabbers, and they almost always end up negative. All right, the second method is even more direct. It's called conduction, which is just a fancy way of saying charging by touch. If you have an object that's loaded with extra electrons, so it's negative, and you touch it to a neutral object, some of those extra electrons are going to flow right over to find a new home. This is exactly what's happening when your charged up body touches a metal doorknob. Zap! The electrons make the leap. Now, you've probably noticed that you get zapped by metal things like doorknobs and faucets. But you build up the charge walking on a carpet or taking off a wool sweater. So why is that? Why the difference? Well, it's all about how easily electrons can move through different kinds of materials. Basically, you can put most materials into two big groups. First, you've got conductors, like metals. Think of these as superhighways for electrons. They can just zoom right through. Then you have insulators, like rubber and plastic. These are more like roadblocks. They hold onto their electrons super tightly, making it really hard for any charge to move. And here's the perfect example from our everyday lives. The reason all our electrical wiring is made of copper is because copper is a fantastic conductor. It gives all those electrons an easy, clear path to travel from the power plant all the way into our homes. It's that electron highway. But obviously, we don't want that electricity getting out and zapping us, right? That's where the plastic coating comes in.
Plastic is a great insulator. It's the roadblock that traps the electrons inside the copper wire, keeping the charge contained and keeping us safe. So you see, conductors and insulators, they work together as a team.
So we've seen charging by rubbing and charging by touching. But what if I told you that you could move charges around and create an attraction without anything ever touching at all? Yeah, this is where things get really, really cool. It's like magic. This process is called induction. So check it out. You start with two neutral metal spheres that are touching each other. Then you bring a negatively charged rod close to them, but you don't touch. That negative rod repels the electrons in the spheres, causing them to flee over to the sphere that's farther away. Now, here's the trick. While that rod is still there, you pull the spheres apart. And just like that, you've trapped the charges. One sphere is now positive and the other is negative, and the rod never even touched them. And this is the secret behind that classic party trick. You rub a balloon on your hair, making it negative. Then you bring it close to a neutral wall. The balloon's negative charge pushes away the electrons on the surface of the wall. They don't leave, they just scooch back a little, leaving the very surface of the wall with a temporary positive charge. And what do opposites do? They attract. And that's why the balloon sticks to the wall. It's pure induction. All right. We've gone through the atoms, we know the rules, and we've seen the methods for moving charges around. We get the balloon on the wall, we get the shock from the doorknob. Now it's time to scale all this up and connect it back to our very first question, and look at the most spectacular light show on Earth. That zap, that little spark you see, it has an official name. It's called an electric discharge. It's simply what happens when a charge imbalance gets so big, so tense, that the electrons make a sudden, desperate leap to rebalance everything. And the bigger the imbalance, well, the bigger the spark. And lightning is just an electric discharge on a colossal scale. Up in a storm cloud, all that churning of ice and water creates friction, building up a massive negative charge at the bottom of the cloud. And just like our balloon in the wall, that huge negative cloud induces a positive charge on the ground below it by pushing electrons away. Eventually, that imbalance becomes too much to handle, and cocoon, the electrons make the jump. That's a lightning bolt. And what's so amazing is that once we understand this science, we can start to control it. A lightning rod is really just a simple metal conductor sitting on top of a building. It offers a safe, super easy path, a highway, for that incredible electric discharge to travel down, guiding all that energy harmlessly into the ground instead of blowing up the building. It's the perfect use of a conductor as a path of least resistance. So when you boil it all down, that's the big takeaway. The tiny, surprising spark you get from your finger and that terrifying, beautiful bolt of lightning from the sky, they aren't just similar. They are exactly the same thing. The same dance of electrons and protons, the same law of attraction and repulsion, just playing out on wildly different stages. It really makes you think, doesn't it? We just saw how a simple imbalance of invisible little particles can create something as powerful and magnificent as lightning. It leaves you with a final question to chew on. What other invisible forces are out there, shaping our entire world in ways we haven't even begun to understand yet?